Hidden in plain sight, a quiet revolution is unfolding inside the machines that power our world. From the smartphones in our pockets to the cloud servers processing billions of transactions, a fundamental shift is occurring in how we build the software that runs our civilization. The most surprising part, this revolution isn't being led by some new Silicon Valley startup, but by an unlikely hero, a programming language created by a small team at Mozilla that's now being adopted at breakneck speed by every major tech company on the planet. Today, we're going to explore why Rust isn't just another programming language, but potentially the most important technological advancement in software development since the invention of object-oriented programming. We'll uncover the hidden epidemic of memory errors costing the tech industry billions annually. How Rust's unique architecture prevents entire categories of cyber attacks. Why Microsoft is quietly rewriting Windows core components in Rust. Amazon's billion-dollar bet on Rust for its cloud infrastructure. And how this language might shape the next decade of technological innovation. This is more than a tech story, it's about how we're finally solving problems that have plagued computer science for half a century. Let's begin. To understand why Rust matters, we need to rewind to computing's early days. In 1972, when Dennis Ritchie created the C programming language at Bell Labs, computers were primitive by today's standards. The most advanced machines had less processing power than a modern digital watch and operated on kilobytes of memory rather than gigabytes. In this constrained environment, C was revolutionary because it gave programmers direct, unfiltered access to the computer's memory and hardware. There were no safety nets. If you made a mistake, the computer would blindly execute your flawed instructions, often with catastrophic results. What no one realized at the time was that this design philosophy would create a systemic vulnerability in nearly all modern software. Fast forward 50 years. And Microsoft's security teams made a startling discovery. Approximately 70% of all critical vulnerabilities in their software were related to memory safety issues. These weren't sophisticated logic errors or complex design flaws. They were basic mistakes, programmers accidentally accessing memory that had already been freed, writing data beyond allocated boundaries, or failing to properly track how long data should remain accessible. The real-world impact of these vulnerabilities has been staggering. The Equifax breach, which exposed the personal data of nearly half the U.S. population, was ultimately traced back to a memory safety issue in a widely used C library. The total cost, over $1.4 billion in settlements and remediation. What's terrifying is that these vulnerabilities often lurk in code for years before being discovered. The Heartbleed bug, for instance, was present in OpenSSL for over 2 years before anyone noticed, during which time it potentially exposed millions of encrypted communications. The fundamental problem is that C and its successor C++ were designed for an era when computers weren't networked and security wasn't a primary concern. Today, in our hyper-connected world where a single vulnerability can compromise millions of devices, we're still using tools built for a completely different technological landscape. This is the crisis that Rust was created to solve. Chapter 2, The Rust Revolution, A New Paradigm. The story of Rust begins in 2006, when Mozilla engineer Graydon Hoare started working on a radical idea. What if we could create a language that offered the raw performance and low-level control of C++, but with built-in safeguards against the most common categories of errors? This wasn't a new aspiration. For decades, computer scientists had attempted to create safe systems programming languages, but all previous attempts came with significant performance trade-offs. Either the language was safe but too slow for critical systems, or it was fast but still vulnerable to certain types of errors. Rust's breakthrough came from three ingenious design principles that work in concert to prevent errors while maintaining exceptional performance. 1. Ownership. The golden rule of memory management. Every piece of data in Rust has exactly one owner at any given time. This eliminates the ambiguity that plagues C++ programs about who is responsible for freeing memory. When the owner goes out of scope, Rust automatically cleans up the memory. No manual memory management required, and no risk of forgetting to deallocate. 2. Borrowing. Temporary access with strict rules. While only one part of the program can own data at a time, Rust allows other parts to temporarily borrow access to that data. The compiler enforces strict rules about how these borrows can occur, preventing multiple parts of the program from accidentally modifying the same data simultaneously. 3. Lifetimes. The compiler as timekeeper. Perhaps most innovatively, Rust's compiler tracks exactly how long every reference to data remains valid. This prevents what's known as dangling pointers, references to data that no longer exists, which are a common source of crashes and security vulnerabilities in other languages. The brilliance of this system is that all these checks happen at compile time, before the code ever runs. It's like having an ultra-precise code review from an infinitely patient senior engineer who never misses an edge case. For developers accustomed to languages like C++, the initial experience with Rust can be humbling. Where other languages might let questionable code compile only to fail mysteriously at runtime, Rust's compiler is famously strict. It refuses to compile code that violates its safety rules. At first, fighting with the borrow checker can feel frustrating, but then you realize every error it catches would have been a potential crash or security hole in another language. It's teaching you to think differently about how memory works. This paradigm shift hasn't gone unnoticed by the tech industry's biggest players. Let's examine how three tech giants are betting big on Rust to solve their most critical challenges. Few companies understand the cost of memory safety issues better than Microsoft. For decades, the infamous blue screen of death has symbolized the instability that can result from low-level programming errors. When Microsoft's security teams conducted an in-depth analysis of their vulnerability reports, they discovered a startling pattern. Approximately 70% of all critical security vulnerabilities in their products were related to memory safety issues. Their solution: begin systematically rewriting performance-critical Windows components in Rust. Starting with low-level networking drivers and security-sensitive subsystems, Microsoft has reported dramatic reductions in memory-related vulnerabilities, in some cases dropping from dozens per year to zero. The beauty of Rust is that it lets us write code that's just as fast as our C++ implementations, but with compile time guarantees about memory safety. For security-critical components, that's game-changing. When Amazon set out to build Firecracker, the secret sauce behind AWS Lambda that enables thousands of lightweight virtual machines to run simultaneously, they faced an extraordinary challenge. Each Firecracker instance needs to start up in milliseconds, consume minimal memory overhead, remain completely isolated from other instances, and do all this while running potentially untrusted code. We evaluated every possible language for this task. Rust stood out because it gave us C-level performance with Java-level safety. We simply couldn't afford the security risks of traditional systems languages in a multi-tenant environment. Today, Rust powers some of Oz's most critical infrastructure, processing millions of requests per second while maintaining ironclad security boundaries between customers. At Meta, engineers faced a different kind of challenge: scale. Their mono-node source control system needed to handle over 100,000 code commits every single day across thousands of developers working on massive code bases. Our original C++ implementation worked. But we spend an enormous amount of time chasing memory-related crashes and performance bottlenecks. The Rust rewrite not only eliminated those issues, but actually improved performance by 35% while using significantly less memory. These aren't isolated examples. From Google adopting Rust for Android to Cloudflare using it in their Edge network, Rust is rapidly becoming the language of choice for performance-critical, security-sensitive systems. The Rust revolution isn't just happening in industry, it's reshaping how we teach programming. Universities that once began their computer science programs with C are now introducing Rust as the first systems programming language. Starting students with C teaches bad habits. It's too easy to write dangerous code that appears to work. Rust forces students to think correctly about memory from day one. It's like learning chemistry with proper lab safety protocols instead of just being handed dangerous chemicals. The importance of memory safety has reached the highest levels of government. In 2022, the U.S. National Security Agency issued explicit guidance recommending memory-safe languages like Rust for critical infrastructure. Many of the most damaging cyber attacks in recent history, from critical infrastructure breaches to military system compromises, have exploited memory safety vulnerabilities. Migrating to languages that eliminate these vulnerabilities could significantly improve our national cybersecurity posture. Perhaps the most compelling endorsement of Rust's reliability comes from the space industry, where software failures can have catastrophic consequences. Both SpaceX and NASA Jet Propulsion Laboratory have begun adopting Rust for flight software and spacecraft systems. In space systems, we can't afford memory leaks or undefined behavior. Rust gives us mathematical certainty about our code's memory safety while meeting our extreme performance requirements. What makes Rust truly special isn't just its technical merits, it's the vibrant, opinionated community that's grown around it. Unlike many languages controlled by corporate interests, Rust's development is steered by an open RFC process where anyone can propose major changes. While other languages struggle with dependency management, looking at you, JavaScript. Rust shipped from day one with Cargo, a built-in package manager that handles dependency resolution, version locking, build scripting, test execution. The result: projects with hundreds of dependencies that actually build reliably. No more works on my machine nightmares. Rust has become the undisputed champion of WebAssembly, the technology letting developers run near-native speed code in browsers. Why? Because Rust's small runtime footprint and predictable performance make it perfect for Figma's collaborative design tools, faster than JS web frameworks like Leptos, even entire game engines running in browsers. From smart thermostats to industrial robots, Rust is conquering embedded systems thanks to no runtime overhead, direct hardware access, community projects like Embassy for Async embedded. For all its brilliance, Rust isn't perfect. Let's confront the elephant in the room, the steep learning curve that's frustrated countless developers. That famous Rust learning curve isn't just a meme. Studies show it takes 6 to 8 weeks for experienced devs to become productive. The culprits: lifetime annotations that feel like type Tetris, the fight with the borrow checker phase, async/await complexities that boggle minds. Rust's thorough compile time checks come at a cost. Those same safety guarantees mean longer compile times, especially for large projects, more cryptic error messages than Go or Python, a steeper IDE setup process. While growing rapidly, Rust's ecosystem still lacks mature web frameworks compared to Django/Spring, specialized ML/AI libraries, enterprise-grade tooling in some domains. As we stand on the brink of a new technological era, with AI systems making autonomous decisions, smart cities managing critical infrastructure, and spacecraft venturing further into the cosmos, the need for reliable, secure software has never been greater. Rust represents more than just another programming language. It's a fundamental rethinking of how we build the digital foundations of our world. By eliminating entire categories of errors that have plagued software for decades, Rust isn't just changing how we code, it's changing what we can trust our code to do. In a world where software controls everything from our bank accounts to our power grids, perhaps the most revolutionary feature of Rust isn't its performance or its syntax, but something far more valuable: the ability to sleep at night knowing your code won't fail in ways you never anticipated. If this deep dive into Rust's revolution got you thinking, I'd love to hear your thoughts in the comments. Are you considering Rust for your projects? What surprised you most about its adoption? For more explorations of the technologies shaping our future, hit subscribe and turn on notifications. We've got amazing content coming on WebAssembly, AI infrastructure, and more. Join our growing Discord community of developers passionate about the future of technology. Whether you're a Rust expert or just Rust curious, you'll find great discussions there. And if you want to support more content like this, the Ko-fi link is below too. Thanks for watching, and remember, in a world of complex systems, sometimes the most powerful innovations are those that help us avoid problems rather than just fixing them. See you in the next one. In Rust we trust. Happy coding, everyone.